All right, so we're actually looking at some information from our planet here. So universal law of gravitation is something that should be applicable everywhere, but I want to bring it down to Earth just for starters, okay? So what we've said in the past is that acceleration due to gravity is 9.81 meters per second squared, and I want to put it out there that that's not always true. That's what it is in this part of the world, in this locality. So when I look at other places in the world, like the equator, when you're at the equator, the acceleration due to gravity is about 9.781, not 9.81. When you're at the North Pole, it's about 9.83. You can see the 9.81 is somewhere in between those two values, for sure. Around Toronto, around these parts, around 9.81. Okay. Brussels, Belgium, 9.811. Actually similar to us where we are right now. And then in Denver, Colorado, it has a little bit of a dip, 9.796. I want to think a little bit about the shape of our planet for a second. And if I were to draw our planet, here we go, we've got the poles, and I'm not saying this is great artwork or anything like that, but, you know, entertain me for a second and draw your picture. We could throw in our equator, and I want to, for lack of a better name, let's call this the side view of Earth, okay? Like if it was like a cutaway of our planet. Side view of Earth. And if this is the side view of Earth, and we found ourselves right here on Earth, and maybe that is where we are. Maybe we're in Toronto, and it's really somewhere around there. It turns out that if you take that point on the surface of the planet, and you take the center of the Earth, and you simply connect the two dots, well, it would be the radius at that point, but that's not actually what I want to get to. What I want to get to is that there would be an angle there. And if you're like me, when I was in like maybe somewhere in grade 6, 7, or 8, I was a young person, and I had a teacher tell me that we were going to talk about geography and we were going to talk about latitude and longitude. And we located places on the Earth based on latitude and longitude coordinates. You guys remember that lesson or whatever? You know, it was part of geography class probably, maybe history. It turns out that latitude is always measured in angles. And I was asking the teacher, why is it measured in angles? Because it seemed to me that you should just measure how many kilometers you are away from the equator, you know, like the arc length, if you like, even though I didn't have the words for it at the time. And they're like, oh, I don't know, we just measure these things in angles. That's the way it was described to me. And I'd be willing to bet that if you asked that question when you were a kid, maybe you didn't get a satisfactory answer. Can you see why we measure latitudes and angles? It turns out that if you want to know where something is away from the equator, this angle here is your latitude. And it also turns out that if I were to take this line that I've drawn from the center of the Earth to that point on the Earth, I could remember this is a cutaway of the Earth, but if I rotated it, wouldn't that trace out a whole level on the Earth? Right? Think three-dimensionally, right? Like if this was a line that could point out of the page and like inscribe on the inside of a sphere, then that angle defines a whole level on the Earth, and that level would be the latitude. And so I don't know why my elementary school teacher didn't explain that to me. Maybe they just wanted to shut me up and move on to other things. Density or something, probably. Anyway, so this is what latitude is. Show of hands, how many people never knew why latitude was angles? Honest answers. It's probably like an honest half the class. That's, you know, maybe it's an indictment of our education system or something, but we really should know stuff like that. Like, I like to ask the question, why? Why do we do things a certain way? We should all continue to ask those questions, no matter how old we get. Anyway, if I take a look at the Earth from overhead, so I know that this is sort of a, I don't know, northern hemisphere supremacy sort of thing, but I'm going to look at it from overhead, thinking of the North as the top, okay? So looking at the North Pole, it turns out that we have this line, and it's not the equator this time. Does anybody know the line that we start our angle measurements for longitude? Yeah? It is the prime meridian, yeah. Prime meridian, where the Great Plains begin. Okay, so here's the prime meridian. And it turns out that we decided to use the prime meridian. Actually, we can again talk about colonial history or whatever. Who ought to decide who the what was the prime meridian and all that sort of thing. I don't want to go down the rabbit hole of that, but there is some colonial history there, okay? There's some world history, and most of it's based on power structures in the northern hemisphere. But what I want to talk about is using that prime meridian as our zero marker. And that zero marker, if you measure an angle, an arc angle, from the prime meridian, I'm going to give that a different Greek letter. Actually, I would like to say theta is for my latitude. I'm going to use phi for, what was that L word I said just a second ago? Longitude, yeah. So this is the longitude angle. Latitude is in degrees. Longitude is in degrees. So whenever you're looking at a coordinate on the surface of the Earth, there should be 2 degree measurements. One's latitude, one's longitude. And then we talk about, now this is the one thing that we maybe didn't talk about in geography class as much when it came to finding locations on the Earth, but it's actually pretty important. If I have a picture of the Earth, I'll do it as a light sketch first, but then I want to throw in the North Pole and the South Pole, and then I want to, like, as I come down the sides, I'm going to put a mountain here and a valley here. Oh my gosh, this is such a deformed Earth, you know? Some knobbly shaped Earth. I'll just make it knobbly on the Eastern Hemisphere. But I've got this knobbly shaped Earth, and we know that these knobbly shapes would be like mountains and valleys and things, right? And so we actually come up with a third coordinate system. By the way, the coordinate system that I'm building right now is called a spherical coordinate system, which makes sense for planets, right? So you can use latitude to locate where you are in terms of like the vertical levels of the Earth, if you like. Longitude would be like this angle measurement away from a predefined zero. And between those two, we can locate any position on the Earth. And we can talk GPS or whatever. But then the third piece of information is altitude. And altitude is, okay, fine, I could locate a place on the Earth using those two variables, but how high up relative to sea level? And that's what we define as being altitude. And so we could also talk about not just altitude, but we could talk about the radius away from the center of our planet. So I'll call that the R value. That's not really altitude. Altitude is how high above sea level. The R value is how far from the center of our planet. So the distance from planet center is R. And then of course that's going to be related to altitude, right? Because slightly different R values are going to be slightly above sea level or slightly below sea level. And so we have these three coordinates, theta, phi, and r, that are going to define any location at any altitude on our planet. So I got the latitude and the altitude here listed out for these different locations. And I also, handy enough, have a graph that's been sketched out. And I'd like to be able to plot that data onto this graph. Now there's a figure title down here, gravitational field intensity versus latitude. So what I'm looking at is the gravitational field intensity here and the latitude here as being the axes of my graph. So we can zoom out ever so slightly, I guess, like to keep it all on screen. And we're just going to graph this out really quickly. You can graph it along with me. So I'm putting in my equator. I've got Denver going in here. Got Toronto. Say it like an American. Toronto. So they always say in the American movies. So you can tell it's not a Canadian actor. And then, of course, the North Pole. And whenever I get a scatter plot like this, I like to do a line of best fit. If I fire a line of best fit through this data, it actually turns out that 4 of these data points line up really well. And then I have this outlier here. Which one was the outlier? Denver. It is. So I'm going to call it an outlier. I've circled it. And I'm just going to name it. That's not very formal. But I'm going to name it as Denver, this outlier. And I've got this little factoid down in the bottom left-hand corner here. I'll bring the graph back. But it turns out that Denver is in Colorado in the US of A. And it's known as the Mile High City. And it actually, you can go there. I've been there. There's a building that has a plaque on it. It's 1,609 meters. I think it's City Hall. And it turns out that that spot is 1 mile above sea level. It's just like a cute little piece of trivia. But they're a mile above sea level. I know we're metric here, but this explains why there's a dip in the acceleration due to gravity or the gravitational field intensity. It's because they're a little bit further away from the center of Earth, as it turns out. Is it a lot of a dip or a little bit of a dip? Little. Answer is little. We're probably not going to set any Olympic records just by holding the Olympics in Denver, okay? Because we've got other issues too in Denver. The air is just a little bit thinner because of atmospheric variation, right? So maybe a little less oxygen make us run a little bit slower too. So it's not like I'm making any, predictions about the Olympics or anything like that if we were to host them in Denver. But it does talk about gravity dips. Another thing about this acceleration due to gravity, and here I am talking about it at gravitational field intensity. In the past, we've talked about AG, acceleration due to gravity, as being 9.81, around Toronto, meters per second squared. But then a moment later, I might talk about gravitational field intensity. Hey, look, I'm going to put absolute values around it, and I'm going to call it G instead of A sub G. And I would write it as 9.81, not meters per second squared, but newtons per kilogram. And I want to talk about what the heck that means. Now, we know that a newton is a kilogram meter per second squared. Well, thank you.
You're welcome.
Appreciate that. Cup of coffee from my favorite Giannotti. Thank you. Don't tell the other Giannottis. Shh. All right. Newton equals kilogram meters per second squared. So if I have newtons divided by kilograms, what happens to those units? Look at that. See how newtons per kilogram really is the same thing as meters per second squared? Now the only reason I really bring this up is because when people are talking about gravitational field intensity, we're talking about how intense the gravity field is. And when you measure how intense a gravity field is, you're talking about what can it do for you? How intense is this thing? Well, it can move a mass with a certain amount of newtons per kilogram of stuff that's there. That's what gravitational field intensity is defined as, is how many newtons of force does this field apply to a kilogram of stuff? While the numbers are both 9.81, this first unit talks about how fast something picks up speed. How fast something picks up speed is a different concept than how many newtons of force does a certain kilogram of stuff experience. You follow the difference? So it really is like a conceptual shift. It's not like it's something we can't understand. So they have different units because they're trying to get at different ideas. But this would be gravitational field intensity. And that also explains why in my table, up at the top of the page, I had meters per second squared, comma, newtons per kilogram. Because I knew I was going to come down to this little explanation, okay? So that's weird to have two different sets of units for the same concept, or the same column. But it's because I wanted to make sure that I circled back to that. Now, I got this shape here. And I want to propose that this is maybe a good cartoon for our planet. People always draw our planet as a sphere, but we have our fact check fella here. Bears, bees, what is it? Bears, bees, and beets. That's it. Anyway, if that means nothing to you, you can go look that up later. This guy knows a lot. Earth is an oblate spheroid. Can you guys say this after me? Like, repeat after me. Oblate spheroid. 3, 2, 1. Oblate spheroid. One more time. 3, 2, 1. Oblate spheroid. Nothing like a geometric chant in the morning, right? So an oblate spheroid is the shape of our planet. We don't live on a sphere. That was always a lie. What's an oblate spheroid? If you want to picture an oblate spheroid like in your mind's eye, can you imagine taking a sphere of jello, imagine that, a sphere of jello, and spin it like a basketball on your finger. Are you picturing it? The shape that you're picturing now is an oblate spheroid. Cool? So it bellies out at the equator, if you like. If I were to say that. It gets big at the equator because of centrifuge effects, actually. But what that also means is, if I take a look at our planet, which is an oblate spheroid, of course, when I go to the North Pole versus, and I'll call that R1, versus when I go to the equator, and I'll call that R2, which one's bigger, R1 or R2 for an oblate spheroid? R2, yeah, everybody says R2. R2 is greater than R1 for oblate spheroids. And if I was going to think about the cross-sectional image here, I'd say, oh, so oblate spheroids have a cross-section that's elliptical. Yes, 100% true, okay? Don't say oval. Oval is like smaller at one end and bigger at the other, like an ova, like an egg, but it's an ellipse. An ellipse is a special shape. It has like its own special properties, right? It's symmetrical, and it's bellied out either end. All right, as latitude increases, gravitational field intensity does what? As you go up in latitude, what's going to happen to our gravitational field intensity? Yeah, it increases, yeah. So I can say it also increases. And I can do a because as we approach the North Pole, we get what? Closer to the center of the Earth or farther? Closer, yeah, closer to the center of Earth. Now, just an FYI about YouTube videos. When you're watching this later, when you're studying for the test or whatever, I just zoomed in. But you know that you can pinch on a YouTube video, you can zoom in on YouTube videos, right? So if you're going back and you're taking notes or whatever and you find that my handwriting's too small, zoom in on the YouTube video. You can always get a little closer, okay? All right, so the shape of the Earth determines how close one is to the center of mass of Earth. This relates to G because objects close to the center of mass, or sorry, I should say objects close to the center of Earth, to the center of the Earth, will experience a stronger force of attraction. Stronger force of attraction. Now, let's think about this. In an extreme situation, here I am on the Earth. I find myself at a certain R value. Call it R1. I could go to the equator and get a little further from the center. Or I could somehow get myself out to this position where I'm off the surface of the planet, right? Floating in space. This brings me up to another question that I had when I was in elementary school. I remember the teacher. He was a great teacher, Mr. LePrad. I liked him a lot because there were a bunch of kids that couldn't afford to be on competitive sports teams. It was just like a family dynamic thing. And he took it upon himself because he had been a fairly competitive baseball player and hockey player in his youth. And every Saturday, he would do baseball and hockey camps with the kids on the weekends that couldn't afford to be on local teams. I thought Mr. LePrad was awesome. Honestly, like, you know when you're a kid and you have like these people that are like your low scale heroes? this guy was an awesome guy. You know, I wanted to make sure that everybody had a chance to learn some nice skills. And it was mostly boys that went out. Sometimes the girls went out too. But the point is, he made the opportunity. And I love Mr. LaPrade. So this is my way to immortalize him, just by telling students, like, you want to be that kind of person in people's lives. Never asked for any credit. And I only found out about it because I had a friend that went to these things. I was on a team myself. My dad was the coach. But Mr. LaPrade always made it happen for people that couldn't have otherwise. And when I remember asking Mr. LaPrade, because we had a question on a test that I got wrong. He said, if somebody's in space, do they experience gravity? And I said, yes, they experience gravity, but diminished. And he said, no, you experience zero gravity in space. And I got the question wrong. And I went back and I challenged it. And in the end, he didn't give me the mark. And I was so, like, you can tell it stuck in my mind. I was so upset about it. Turns out I was right. But can we talk about why? How do we know? Does gravity disappear just because you're off the planet? No. There's this thing called microgravity. And microgravity doesn't mean that it disappears. It's just very diminished, right? We're going to be out there. That radius gets big enough. The gravity doesn't disappear. It just gets diminished, you know? So, like, you know, even our heroes make mistakes sometimes. Mr. LaPrade, heck of a guy. I want to make sure that we get this, though, before we walk away. Meters per second squared is acceleration due to gravity. Newtons per kilogram, that's gravitational field intensity. But the reason that the numbers can be the same in our table is that kilogram meters per second squared divided by kilograms is equivalent to meters per second squared. And that's why it's okay for us to have the same numbers. Okay, we're getting at different concepts, and it's okay for there to be the same numbers.